I want to discuss in this video in more details the mathematical reasoning that goes behind constructing decision trees. And some of the key concepts that I discuss in this video are about different types of impurity measures and about data splits. And I want to start with this observation that the problem you are trying to solve is that you are given a dataset and you would like to build a decision tree for that dataset. And obviously, you can have many different datasets, and in principle, you would like to have the smallest one. So, for example, the tree that has the smallest possible depth, or said in a different words, the decision tree that has the fewest number of leaves in that tree. And this is a problem that's known for a long time already to be computationally very difficult. And in fact, this formulation of the problem where you ask, do I have a decision tree for set X with depth at most W, where W is a parameter, we know that this problem is NP-complete. So that means that the way the complexity of the algorithm grows in terms of the size of the training data set is exponential. So what that means in practice is that you cannot hope to build the minimal decision tree for a realistically sized data set, and instead what you do is you take a heuristic, you take typically a greedy type of construction where you say, I cannot build the smallest possible decision tree, but I'm going to build one that hopefully is not going to be too far from it, and anyway is going to be fast. And to achieve this idea that you're going to have a fast construction, the greedy approach is essentially saying, I'm going to build this node by node, top down, starting from the root node, and in each node, I'm going to make what seems to be the best decision. And this is the part that I'm going to open up in more details when I switch to impurity functions. You have this idea that you would like, in principle, to end up with so-called pure nodes. If you think about a classifier, a pure node would be one where all the data points that reach that node are from the same class. In that sense, you talk about purity. If you have a regressor, the idea is that all the training data points reaching that node have values that are very close to each other. So in that way, having these pure nodes eventually in the leaves of your decision tree is going to make the problem of giving a prediction very easy, because they are either from the same class or, in the case of a regressor, they essentially have the same value. So in each node, as you build your tree, starting from the root and then splitting the tree and adding more branches, in each node you are going to make a decision about how to split your data set, and you are going to take the split that seems, based on the data set that you see in that node, seems to advance you the fastest towards pure nodes. And this is how this is done. So in principle, you have a training data set. As usual, we are starting from this idea that you have a training data set. I'm denoting this by X, and this consists of a number of data points and their labels. And let's say that we have n data points. And these labels, because I'm discussing first classifiers, these labels are going to be one of, say, k possibilities if I deal with k classes in my problem. And when you are considering, you are in decision in the node M, let's say, for your decision tree. So you are starting with node 0 in the root, but eventually you are going to be in node M. And so for node M, what I'm going to make a few notations in here. So first of all, I'm going to say, how many data points do I have reaching that node? And I'm going to denote that by nm. And for the root, this is the entire training data set that you have. So you are starting with that, and you're going to split it in smaller and smaller sets. So in node M, nm is the number of data points reaching that node. And also I would like to make some notations for how many data points I have reaching M from each one of those classes. And I'm going to denote this by n, so the number of data points in node M coming from class K. So this is going to be for all these classes from 1 to K. So again, this is going to be about the number of data points in node M from class K. And so what you do once you have, once I have these notations, then obviously you can make now an estimation for the class distribution in node M. So how many data points, and so what's the probability of each class based on the data set that you see in node M. This is going to be, so class distribution in node M. This is going to be simply just, it's going to be an estimate, so I indicate this with a hat. So it's going to be an estimate for class K, given the data set that I started with, and given that I make this estimate in node M. So this is simply just, how many data points I have from class K divided by the total number of nodes. And all of this is relative to node M. And just to simplify this notation, I'm going to just denote this and say, this is the probability in node M of class K. And so this is going to be for all classes from 1 to K. And so, I mentioned, the idea of pure nodes. So pure node, so you would have a pure node in case one of the classes, all the training data points in that node are from a single class. So one of the classes will have probability 1 and all the other ones will have probability 0. So one way to write this in a compact way is just by saying, hey, you are pure if all of these probabilities are 0 or 1. And obviously that's going to mean that exactly one of them, is 1 and all the other ones are 0. And so, the whole discussion I want to have in this video is, how do you reason about the best decisions to split your data set and to create, nodes in your tree? And what's going to drive us is going to be some measure of impurity. And there are several, options for this, and I'm going to discuss them one by one in this video. So, but the idea is that you will have some sort of a numerical measure of impurity, and what you want to achieve is, this measure of impurity. First of all, it should be non-negative. So you are going to take care when you define this measure that it's a non-negative function, and you would like it to reflect, for pure nodes, you would like this to be 0. So for pure nodes, the impurity should be 0, and you would also like to define it in such a way that the lower it is, the closer to purity your node is going to be. And so if you manage to, introduce such a measure of impurity, the algorithmic idea is going to be, okay, so you have your entire training data set in the root node of your decision tree, and then you are going to look for ways to split your training data set, let's say in 2. It could be in principle even for more, but typically you are dealing with binary decision trees, and part of your training data set you are going to send to the left branch of your tree, and the other part of your data set goes to the right branch of the tree. And so that means you create 2 new nodes, and you would like to see a drop in the impurity. So you had whatever impurity you had in the root node, and then you have these 2 new nodes which are successors, and the total impurity in these two nodes, you would like it to be lower than what you had in the root node. And so you have this idea that as you make decisions on how to split your data set, the impurity overall is going to get lower and lower. Eventually it's going to get to zero. And when it comes to you deciding what kind of split to make, you are going to make the split that gives you the biggest drop in impurity. And these are ideas that I'm going to come back to after I show these impurity measures. So let's take a look at several examples of impurity measures. And the first one that I want to discuss is the so-called Gini measure. And the idea of the Gini measure is that you would like to have some sort of a measure for the probability of misclassifying a random sample in node M. So for node M, you want to reason about what's the probability of misclassifying a random sample in this node. So you start reasoning about this and you realize, I mean, there are two components in here. One is you have to pick a random sample, and then you have to pick, a prediction for that random sample, and then we are going to discuss about, how likely are we to make a mistake and misclassify this. So the part with picking the sample, so picking a random sample, remember that you have k classes, and the probability that it comes from class K is exactly what we denoted on the previous slide by this PMK. So probability in node M that you have it coming from class K. And then the other one is pick a prediction to give. And this prediction, you are also picking it with the same sort of probability distribution that you compute in node M. So you say, okay, so I'm going to give us a prediction class K prime, and the probability for class K prime is this that we have computed for node M, and so it's PM K prime. And so the probability that you are correct, so you are correct. So the probability that you are correct is exactly the probability that K, which is the real class of that sample you picked randomly, is exactly the class that you gave as a prediction. And because these two picks are random and they are independent of each other, so that's going to be exactly the probability for the first peak and times the probability of the second peak. And now I'm not writing K prime, but I'm writing K because it's exactly the probability for K equal K prime. So that altogether gives us that the probability that I'm correct about, giving a prediction about giving a random prediction to a random sample is exactly PMK squared. And so the probability that you misclassify, which was the thing that we were trying to compute, so you misclassify with the probability 1 minus, this, but remember that you have k possible classes. So it's going to be 1 minus sum from 1 to capital K of this probability that you were correct for this class. And so, and this is exactly the definition that you give for the Gini. So Gini index or Gini impurity, it's also called. So impurity for node M is defined to be exactly what I calculated here in terms of the probability of misclassification. So it's exactly 1 minus sum from 1 to capital K by PMK squared. And, just to check that this is indeed a good function, I mean, with respect to what we wanted and what we wrote on the previous slide. So, for example, for a pure node, remember that the probability of the class is one class comes with probability 1 and all the other ones are coming with probability 0. So in that sum I have exactly 1, 1 and the rest are 0. So the Gini index for a pure node is going to be 1 minus 1 squared, so that's exactly 0. And that's something that we wanted, and we stated as an objective for when we define a measure of impurity. If we take another example, and we say, hey, how about if you have a perfectly balanced node? And what I mean by that, you have the k classes consisting of exactly the same number of points, so perfectly balanced classes, or if you want perfectly balanced data set in node M. So that would mean that really all of these probabilities PMK are exactly 1 over k. So in that case, the Gini index is going to be 1 minus, and you realize that you have 1 over k squared, but there are k terms in that one, so it's going to be 1 minus 1 over k. And so Gini index is indeed one of the most popular measures for impurity. And again, I'm going to comment and I'm going to show you visually how it behaves for different distributions of your data set in between the classes. But before that, I will introduce another one so that we have a term of comparison. So another popular one is the entropy, and the entropy is well known, coming from information theory, and it was introduced as a sort of a measure for how much a random variable, how much uncertainty it contains, or how much surprise, if you want to see it the other way. And it also, gives you a measure for the average amount of information that you need to identify the outcome of a random event. So if I'm just writing this, so information theory defines this entropy as being, so this is an entropy for a random variable. So intuitively it's defined, it's a measure for how much uncertainty or surprise, if you want, is in that variable. And the way this behaves is that the higher the entropy, the more random and less predictable the event or the variable is. And the lower the entropy, the more certain and more predictable the event or the variable is. And the typical, definition of entropy for a discrete variable, so for a variable that takes values from 1 to k. So typically this is defined in information theory as being h of x is sum from 1 to k, so you sum up over all possible values, and you have this, it's the probability of seeing value k times logarithm of this probability. And that's exactly how the entropy is defined also when it comes to impurity measure. So if I want to define entropy as an impurity measure, and so this would be in our decision tree defined for a node, let's say for node M. So this is defined as h of M is going to be sum. You have your capital K classes, so you have a sum over all possible classes, and you are going to have a sum over the probability of class K in M times logarithm of this probability, Pm of K. Entropy is also a very popular choice, and there are some differences in how it behaves if you think about it, with respect to the Gini impurity. And again, this is going to be one of the benchmarks that I show visually in just a couple of minutes. I show just one more impurity measure for a classifier, and that's the misclassification error. And here the idea is that you would like to think about how many data points in a node are likely to be misclassified. So the focus is going to be, when you introduce this function, the intuition or the metaphor for introducing this function is you want to know how many data points in the node that you're looking at will be misclassified. And so, I mean, when you say this, you have in mind, a certain strategy for how to give predictions in that node. And the intuition we have here is that we are going to give as a prediction the label of the biggest class in that node. So this is going to be a sort of winner takes all. You have several classes, you measure, the probabilities of each classes, and the class that dominates is going to give the prediction for all the data points that reach that node. And so with this decision, so the prediction in this class is going to be this one. You say, okay, I'm going to look at the probabilities of my classes, and I'm going to take the maximum probability. And that's if this maximum probability is reached by class, say 3, then I'm going to give 3 as the prediction for all the data points that reach this node. So when you think about how many data points will be misclassified, this is really about the fraction of data points that are not in the majority class. And so the way you introduce this impurity measure is going to be simply E of m is going to be 1 minus, and so you say is the fraction of data points not in the majority class, and the majority class is exactly this one, or the probability of the majority class is this one. So that's the misclassification error defined as an impurity measure. And so again, you are checking, for pure nodes, you have one class with probability 1, the other ones are 0. So obviously the majority class will have this this probability 1. So that means that E of m is going to be, in this case, 1 minus 1. And that's 0, so that's exactly what we wanted. And for balanced nodes or perfectly balanced nodes, the misclassification error is going to be 1 minus maximum, but all of them are having exactly the same probability, and that's 1 over k. So, I mean, this is feasible as a measure of impurity. In practice, this is in fact rarely used as an impurity measure, and I have this plot to show on the next slide. Why that's the case? I just comment here verbally. The point is that for almost pure nodes, where you have one class that dominates by far all the other ones, but the node is still not pure. This misclassification error doesn't really notice that even small changes in how you are doing the split will not really change much this misclassification error. So as a driver for further splits, this is not really a good choice in that case. Another one is if you have some small changes in your data sets that lead to small changes in the class probabilities, again, you will not see this in the misclassification error because it's dominated just by the majority class. All other changes that reflect in the minority classes will not be visible into this one. However, it is useful as a thought and as a function, but it's going to come back in our discussion when we discuss about optimizing decision trees in terms of pruning decision trees. But here you have it. If there is a case sometimes for such an impurity measure, it's certainly a valid choice. So I have this slide where I just want to show a comparison. And the comparison here, the plot is done for a binary classification problem. So we only have two classes. And on here on the axis, I have the class probability for class 1. So 1 minus this one would be the probability for the other class. And here I have a measure of impurity, and I'm displaying these three impurity functions that I showed for a classification problem. And we have in blue the entropy, and we have in orange the Gini impurity, and we have here in green the misclassification error. Now, if you have more than two classes, the plot is often very similar as this one. It's going to be a little bit more difficult to show visually, because for a ternary classification problem you would like to show this in 3D, and then it becomes more difficult with more classes. The point is that this entropy has the steepest descent. So as you come to the extremes, either you have class class 1 in our case very small, so the data set is dominated in node m by the other class, or in here the drop of this entropy is really quite significant. So what this means is that as you are coming to these more extreme cases, the entropy might push harder than the other measures for pure nodes, because it has still quite a big drop in what it measures in terms of impurity. This is a little bit softer for the Gini, so there is less of a drop, and in fact if we had more classes you would actually see even more the difference between these two, how much softer the Gini impurity is. So Gini impurity, I mean, if you build it all the way, surely it's going to give you pure nodes, but if you stop early the construction of the decision tree, the Gini impurity might lead to larger leaves that still have some small impurities, not as drastic as the entropy to push to pure nodes. That being said, they are quite similar in practice, and if you look, for example, at the structure of the trees that you obtain by using either one of them, or if you look at the size of the trees that you get, for example, by early stopping, and you ask, would there be a smaller tree with one or the other one? In practice, they turn out to have very similar behavior in terms of what kind of output they give, what kind of decision trees they build. One other comment I want to make in here is that even though in the case of the binary classification, the entropy has a maximum value of 1, this is not the case for ternary or more classes in your problem. The entropy can in fact have values more than 1, whereas the Gini impurity always has values just between 0 and 1. And the misclassification error in this case of the binary classification has a maximum of 0.5. But I mean, the line for the misclassification error is going to be much flatter as you have more classes, because the majority class, in this case, it wins by having as many as 50% of the data points. But if you have more than two classes, it can win with a smaller percentage. So it can win with having just a little bit over 1/3 in the case of the ternary classification and so on. So this misclassification error, this is one of the reasons why is not that useful as an impurity measure. It's a much flatter function than Gini and the entropy.